Okay, so we want to again welcome everybody to tonight's webinar. This is the July 21st non-event, the kind of the night that nothing happened and we were all expecting something to get going. I'm Joe Deli Carpini, the Science and Operations Officer, and with me is Rodney Chai, one of our meteorologists. And Rodney will be taking us through the presentation tonight. It's not too long, and then I'll come back and we'll go through our weather briefing. So Rodney, with that, I will hand the floor over to you to go through this event review.
Well, thank you very much, Joe, and welcome everyone to tonight's webinar on the non-event a few weeks ago. So the models were forecasting storms across much of southern New England that afternoon into evening, with the potential for severe weather across parts of Connecticut, Rhode Island, and southeast Massachusetts. And what initially drew our attention to this severe setup was that, so there was an upper level trough, so think about 18,000 feet above sea level. So you have, a trough, and that would basically kind of swing across our area. And when that happens, it tends to draw instability or moisture northwards from the mid-Atlantic states. And so the models were all indicating that this trough is going to go negative. And so if you're not sure what is negatively to the trough, basically it means that the trough axis goes from northwest to southeast. And typically, we want the trough to go negative in order to have stormy weather, not just in summer, but also in winter. But in reality, so the storms actually pass well offshore of New England. And so what happened was that the trough actually did not go negative. It dropped south very early on in the day and shifted the wind to the west-northwest all the way to the Cape Cod Canal by early afternoon. And that is actually not a wind direction you want if you want storms. And so I was working that day and I saw the winds switch to the northwest earlier than expected. So there was kind of like a gut feeling that maybe the storms would not produce. And sure enough, that happened. But hindsight is 2020, and I can tell you that all the guidance we were looking at were very bullish with the storms. And when that happens, I mean, when you have like near uniformity of the models showing you the storms are going to happen and they're going to be pretty robust, it is very difficult to go against that. And eventually, later that evening, a few storms did develop with the actual cold front. And some of you may remember that there was one severe thunderstorm warning that evening, and multiple marine weather, special marine warnings. So that was a case of it was a little bit too late in the game when the actual cold front came through, and that's why the storms did not develop as expected. So let's take a look at some of the Storm Prediction Center graphics that were issued beforehand. This was day 2 outlook, and you can see there was a slight severe risk for pretty much for the eastern half of southern New England. So that includes Hartford, Providence, and Boston. And the main threat for that was straight line wind damage, but there was also a low probability of tornadoes as well, and also the risk for some large hail. So so it was from 2 days out. I mean, day 2 outlook, the SPC was also pretty bullish with the severe weather threat across southern New England. And this is day 1 outlook. And this was actually issued just before the storms were expected to happen. And so you can see the SPC maintained a slight risk, pretty much the same area. It did take out the tornado risk, but it still have the straight line wind damage and large hail. And this is the surface analysis. And So this was the at 8 a.m. Trough Z. So you can see that. So basically, that dashed line you see across eastern Massachusetts into Rhode Island, that's what we call a surface trough, and these features tend to be, they are more subtle than like a cold front or warm front, where the temperature, dew point, and wind direction behind and ahead of the front are quite distinct. But in this case, you have a very subtle trough axis that moved through very early on in the day. And what happened with this development is that the wind direction shifted from the south or southwest to the northwest. And once again, that's a wind direction that is unfavorable for forming storms, in the summer, and because that brings in dry air from the west, and basically that kills off any budding updrafts or any upward rising motion of air that could potentially form storms. So, and you can see that the dew points, and that is the number at the bottom. So you can see low 60s behind the trough, and near 70-degree dew point ahead of the trough. So that is another indication that a warning sign that the storms may not perform to expectation. And this is the surface wind streamlines analysis, and you can see when the trough actually moved through our area. So basically, the winds were initially from the southwest, from the west, but then eventually they turned to the northwest, and that brought in the drier and cooler air behind the trough axis, and once again that greatly diminished the probability of storms forming. And let's take a look at some model guidance, and this is the HREF. It's an ensemble guidance of some of the most trustworthy short-term high-resolution guidance that we look at. And this graphic specifically uses a paintball analysis, and so all the different colors on the graphic, those are individual high-resolution models. And when you see there's a kind of like a uniform color shading on this graphic, it goes to show you that the individual high-resolution guidance converge with each other. So that increases our confidence that in the solution, in the outcome, because when we see individual members agreeing with each other, it means that there's a higher probability of that outcome being relevant and actually occurring. And this is taking a look at the 24-hour maximum reflectivity. This might look like a rainfall map, but it's not a rainfall map, but per se. What it actually indicates to you is the area where the highest radar reflectivity occurs. And typically when we see, if you look at your radar or your app or on our website, when you start to see yellow shading or red shading, that is indicative of not only heavy rainfall, but also where the upward motion of air is the highest. So that indicates that you can see that pretty much of southern New England is under the gun for potential strong to severe storms. And this is again the HREF depiction of the surface-based CAPE or instability above 1,000 units. So so when you have surface-based instability above 1,000 units, that indicates that there is sufficient instability to form storms. And you look at this is the probability of instability above 1,000 units, and you can see that especially across eastern Massachusetts into Rhode Island, the probability is between 70 to 90%. So that's pretty high probability. And there's even also some probability of the Cape over 2,000 units. And again, the axis of highest probabilities across eastern Massachusetts into Rhode Island. And in this case, we are looking at about between 40 to 60% probability of Cape above 2,000 units. And this is taking a look at the maximum 10-meter wind speed overlaid with where the reflectivity is over 20 units. And so, you know, not only do you want high wind speed in this case, but also you want it in the area where storms are actually occurring. So in this case, you can see the highest probability is across southeastern Massachusetts into Rhode Island and into parts of southern Connecticut. And this is taking a look at the 0 to 3 kilometer storm relative helicity, and which is the spin of the atmosphere. And you can see that they are kind of between 50 to 100 units of storm relative helicity. And that was actually why the SPC put out a 2% probability of tornadoes. So low probability of tornadoes, but non-zero chance of tornadoes. And this is taking a look at the hourly rainfall output, and you can see that you know, the HRF depicts a line of heavy downpours associated with the thunderstorms around late afternoon into early evening hours. So, you know, once again, the HRF is an ensemble guidance, so it takes into account the different individual members. So, you know, when we can see a line like this across southeast Massachusetts into Rhode Island, that again lends confidence into storms actually forming. And this is taking a look at one of the members of the HRF, the HER guidance. And you can see the HER is pretty robust with that line of storms actually bowing out as it crosses into Rhode Island and southeast Massachusetts. And when you see a line of storms bow out, it means that there is potential for damaging straight line winds. And this is yet another member of HRF. This is the NSSL model. Again, a very skillful model. And again, while not as robust as the HER, it tries to show the same idea that basically the storms would kind of form into a line as they get into eastern Massachusetts and Rhode Island. And so with all the models, you know, pretty much agreeing that we're going to see, not only are we going to see storms, but we're going to see potentially severe storms with damaging straight line winds, we went ahead to, you know, to message our emergency managers and partners. This was the one page that we sent out to the emergency managers, and you know, we basically gave them a high-level overview of what to expect, the timing, the hazard and impacts. And we did say, you know, one of the forecast challenges was the aerial coverage of the severe storms, but nonetheless, the greatest risk for severe weather is across eastern, southern New England. And so that's, you know, the greatest risk between 1 to 9 p.m. And we did put out a special weather statement out ahead of the potential storm development, just to give people kind of a heads up and awareness. You know, if you had any plans for outdoor activities, be sure to keep an eye to the sky, and definitely be sure to head indoors if you see the storms coming or hear thunder. And it seems that by late morning everything seems to be going to plan. Storms began to fire up in the mid-Atlantic states, and that was pretty much in line with the models. And around mid-morning, the SPC highlighted the likelihood of a severe thunderstorm issuance from Washington, D.C. all the way into southern New England. And in the Weather Service, we emphasize the importance of collaboration, and we collaborate a lot with the Storm Prediction Center, and we talk to them, and we kind of discuss, should we actually issue a severe thunderstorm watch for parts of our area. And the consensus is that we, even though we are, not sure on the northern extent of the severe storm coverage, we did decide to, put it into Boston and Providence corridor, because it is, it is ultimately a watch, so you kind of want to give some padding or buffer in addition to the areas that you're highest confident, that you're most highly confident in. So that's why it was extended all the way to the Boston Providence corridor. So, and that is the Trough PM update, and so the SPC issued a mesoscale discussion, and kind of shows you that the front is kind of set near the Massachusetts-Connecticut border, and the best instability would be located near and south of that frontal boundary. So, and that is kind of in line with the thinking of the area coverage of the severe thunderstorm watch. And so, and this is, let's see, within the watch area, so the confidence highest closest again to the kind of just a little bit south of Boston, so the Providence into Plymouth corridor. And once again, even though we are less confident in the storms going into Metro Boston and Northern Rhode Island, they were included in the watch because of the importance of kind of giving yourself some leeway or buffer. And this is just before 3 p.m. So by that time, the storms were still kind of going strong across Pennsylvania into central New Jersey, but there were some initial signs that the storms may not perform to expectation. We started to see some what we call SIN, or inhibition, and when the atmosphere is inhibited, it tends to reduce the likelihood of the air rising into the atmosphere and storms forming. And we started to see these signs across southeast Connecticut, Rhode Island, and southeast Massachusetts. And there were some rogue storms that kind of spilled into our area, but they kind of weakened. So so those were kind of like red flags that again, it would not, the models probably overdid the convection, and the storms will not perform up to expectation. And this is just before 4 p.m. We try to be as proactive as we can. So in this case, we kind of saw the red flags, and we trimmed back the northern edge of the severe thunderstorm watch. Ended up removing northern Connecticut, northern Rhode Island, and Boston metro area from the watch, but we left the remaining area intact and until 8 p.m. So because there was still the reduced likelihood of seeing some destabilization across the southeast zones of our coverage area. So, and additionally, there's also the concern that the sea breeze boundary may help become a focus for development of storms. And this is at 5 p.m. And at that point, we are pretty much on the verge of dropping the severe thunderstorm watch. So the analysis shows that the front has sagged well south, and the wind has, behind the initial trough axis, has worked its way all the way into Cape Cod. And so when that happens, the northwest winds are limiting surface convergence across southern New England. And in addition, there's also dry air making its way into the region, so that further diminishes the chance of storms forming. And 6:30 p.m. Update, we finally made it official that the severe thunderstorm watch has been dropped for southern New England and the coastal waters. So looking back, there's only a couple of severe reports in southern New England, and I believe one of the reports actually ended up verifying the only severe thunderstorm warning that we issued that evening. So you can see this is just a radar loop of what actually happened. You can see kind of pretty much slim pickings for much of the area, but then eventually, as we headed into the early evening hours, some storms started to form along the actual cold front, and you can see the blue polygon, that's special marine warning, which is the type of warning that we use to warn mariners of possible 34 knot gusts and above. And then eventually we did also issue that one severe thunderstorm warning, which is depicted by the yellow polygon, for parts of the metro Boston area into northern Plymouth County. And this is taking a look at the red, green, blue satellite imagery loop of how the storms in Pennsylvania track to the east, but not to the northeast. So we ended up being kind of on, on the fringe of the real action, just too far north. So going back to the model guidance, this is again the HREF model, and see this is taking a look at the 500 millibar wind, and that's basically the level that we look at, the trough axis, the ridge axis, and 18,000 feet above sea level. So you can see that the HREF tries to show the trough going negatively tilted, and so the trough axis from the northwest to the southeast, that's a negative tilt. But in reality, the trough never really went negative, but it was more of neutral. So it was just more like a north to south orientation. And when that happens, when the trough does not go negative, it tends to force the storm activity well to our south, and we ended up being high and dry. So in summary, so the models, we hope to show you that there was more than enough evidence that the models were forecasting storms across much of southern New England, with the potential for severe weather across the southeastern zones. But in reality, nothing happened, save for some, strong storms across the waters and parts of the Boston area. And a key reason is because the 500 millibar trough never became negatively tilted. it remained neutral, and the convection passed well offshore of New England. And at the surface trough dropped south very early in the day, shifting the winds to the west or northwest, crashing the dew points and drying out the atmosphere all the way to the Cape Cod Canal. And when that happens, the surface convergence is minimized, and because the air is dry, it really limited the possibility of storms forming. And eventually, in the evening, a few storms did develop with the actual cold front, but it was nothing severe enough to warrant a severe thunderstorm watch in the afternoon. And with that, I will pass it back to Joe.
All right, thanks, Rodney. And looking at that 500 millibar chart, and actually, let me see if I can. I can't get back to it very easily, huh? I guess not. Okay. When we have that upper trough, what it showed there was almost like when we miss our snowstorms, Rodney. It stays neutral and moves everything out to sea south of us instead of going negative and drawing everything up here. So it was almost like a wintertime situation. It's rare to see those in the summer, but yeah, I guess they happen too. All right, so let's see. Got some questions here, and then we'll go on to we'll update on the radar and go over our weather briefing. So let's see, from John. Did the guidance from the high-res models change that morning with the wind shift in the east? As I remember, Rodney, I don't think they did. And the HREF, the nice thing about that is it gives you the latest run, but it also includes the previous run. So there was some thought that maybe the previous run was kind of weighting it down too much and the current run had backed off, but that really wasn't the case. The one model, the HRRR that we showed, runs every hour, and eventually it did pick up on it. As I was working with Rodney that day, so I think it was around lunchtime, Rodney, that it finally started to pick up, that we weren't going to get much. But we weren't too sure about that, simply because sometimes the model has a tendency, it'll lose the storms for a couple of hours in like the 6-hour time frame, and then they'll come back. So we weren't sure if that was just a kind of a blip in the model, or if it really was onto something. It turns out it was onto it. So it was the only model that really picked up on it. I think it was around noon or even 1 p.m., if I remember that correct, Rodney.
Yeah, I think that's right, Joe.
Yeah.
I mean, it was by the time the models picked up on the drying trend and the northwest flow. I mean, by then it was too late.
Yep. And then follow-up from John, what if any signals in the days leading up to the non-event hinted at the non-development of storms? There really wasn't much. Usually you'll see, one or two models that don't have much going on, but they all kind of were in good agreement for one reason or another that we were going to see, storm development here. I think they all latched on very well to the activity in Pennsylvania and New Jersey and did show that heading offshore south of us, but also at the same time develop more activity up further to the north. That just didn't happen. So there really weren't a lot of what we call red flags going into this that's saying, oh, well, a couple of models are showing nothing happening and, maybe that's going to happen. It really was all of them just kind of, developing the storms too much over our area when in fact, the moisture, the instability was really limited to our south, and the fact that that upper trough kicked everything east, that just was kind of the nail in the coffin for this event. So really not the usual signals that I would have seen in the days leading up to it, John. Let's see, from Landon, the update stated that mid-level drying was occurring, and this could be seen in the K-index fields. He's asking, what are the K-index fields, and would it have been possible to forecast a change in mid-level humidity? So the K-index is one index that it kind of shows the mid-level moisture, to keep it simple. So when you have higher values, and typically when you're getting up into the 30s with the K-index, that's when you have sufficient moisture. In this case, we had seen the drying, but sometimes you don't necessarily need that either. That's not a required element. It's helpful, but it's not always required. So you can see that in the model forecasts, and I don't remember, Rodney, if we had seen any forecasts of lowering, or decreasing in the K index that day. But my guess is it probably was there. But again, it's not something that you lock onto like you would for instability or other things. But it's certainly, if it's there, you definitely have more moisture and it's more favorable. So yeah, in hindsight, maybe we could have put a little more weight on that, but you don't always have to have the K index in there. But for organized storms, yeah, that's a definite signal. So Rodney, I don't know if you have anything to add for that.
Yeah, Joe, I think, in London, thanks for the question. As far as I could remember, the models were all showing K indices above 30. And the only time I saw the K indices, dropping into the 20s was actually was looking at real-time SPC metal analysis. And again, that was, because if the models believe that the K index is going to be 30 or above, of course they're going to generate storms in the output. But in reality, that's why metal analysis is so important. But this is a situation whereby by the time we realize that the mid levels are drying out, it's kind of a little bit too late in the ball game. So and that's why it was we know it's disappointing for a lot of people, but it was also very disappointing for us as well. But we did do our best.
Okay, we have the next question is from Robert. Can you explain a negatively tilted trough? And he wants me to bring up the chart. So I can do that. Let's see, let me call it up here. Okay, so you're seeing the loop again that Rodney just showed, Robert. And on the left is an example of a trough going negative. And you'll see us refer to this more in the wintertime because it's really something that we watch for winter storms. So if I take my cursor and I draw my line through the axis of the trough, so think of the lowest part, kind of that U shape. It starts off this way, but then as it comes over New England, notice how the axis shifts going from southwest to northeast and then going northwest to southeast. So this is going negative. See how the curvature changes? It kind of goes on this kind of axis as it goes. It's rotating through New England. So that's what we call a negative trough. Now, if you look on the lower right, this is the analysis. And you can see the trough axis doesn't change very much. It's actually going more north to south. And that's what we call neutral tilt. It's neither positive or negative. So positive tilt is what you see in the Great Lakes here, the axis going southwest to northeast. Neutral is straight north to south, and then negative is northwest to southeast. So in this case, the models were forecasting it to go negative, which would have drawn more moisture up here and probably a lot of those storms in Pennsylvania and New Jersey. But in reality, on the right, the trough was neutral, straight north to south as it crossed us, and it kicked. What that does is kick everything out to our south. So you'll see a lot of times with our winter storms, we'll talk about that. We need that negative tilt to get that moisture up into our area for New England, as opposed to being neutral, where it kicks everything out to sea. And that's when we miss our storms. The storm might track off of the mid-Atlantic coast and out to sea. So I hope that helps, Robert. If not, just drop another note in chat. Another Robert wants to know about 95L. Oh, we'll get to that in a minute. Hang on, Robert. And the other Robert says that works, so perfect. Okay, John wants to know what causes convective inhibition with the blue shading. So convective inhibition is just, think of it as the opposite of when we show our cape, showing the instability. It's kind of a cap. So when we show our soundings, we show a cap. It's kind of a lid. So think you're boiling a pot of water on the stove. If there's no lid on it, all the steam can go straight up, and that's our convection. It's going straight up, and eventually it'll condense. If you put a lid on the pot, that's a cap. So none of the air is going to be able to escape. It can't get up higher in the atmosphere. It can't condense. It can't form into clouds, showers, thunderstorms. So just think of it that way. If there's a lot of that convective inhibition, then we can't get those big updrafts to grow, and we can't feed on that instability. So John, I hope that's in simple terms for you. That works as well. So let's see, Rodney. That's the end of the questions for now. So if you have any others, go ahead and drop them in the chat.